Alright class, let's go ahead and start doing the math problem. I'm using the reference book McGraw-Hill Thermodynamics book 8th edition, Thermodynamics and Engineering Approach. So I'll solve this problem 7.21. So this problem is based on the topic 7.2 that we talked about previous class, that entropy principle. So this problem 7.21 problem is telling us that heat in the amount of 100 kilojoule is transferred directly from a hot reservoir at 1200 Kelvin. So that means that you have a hot reservoir, right? That hot reservoir temperature is 1200 Kelvin, and the heat transfer is 100 kilojoule, right? To a cold reservoir. Cold reservoir is nothing but a sink, right? So if you have a sink, that sink temperature is 600 Kelvin. Calculate the entropy change of the two reservoir and determine if the increase of entropy principle is satisfied. So first thing is that we have to determine that what is the entropy at of the two reservoir, right? Entropy entropy of two reservoir, right? And the second thing is that it's asking us that increase of entropy principle, is it satisfied or not, yes or no, right? So let's go ahead and do the measure the or calculate the entropy at two different state. So state 1 and state 2, right? Or for thermal reservoir 1 and thermal reservoir 2. So we discussed about the sign convention of the thermal reservoir. So if in any thermal reservoir, if the heat is output, then it will be negative, right? So this is negative, and heat is coming here, or heat is input, 100 kilojoule heat is input for this reservoir, right? For the sink, then it will be a positive quantity. So for now, we know that entropy formula for example, for thermal reservoir 1, or let's consider this one is state 1, or for the source, right? Source entropy is nothing but Q over T. However, this Q is negative here, right? So heat is 100 and the temperature 100 kilojoule, right? And the temperature is 1200 Kelvin. So the entropy S1 at state 1, it will be negative 0.083 kilojoule per Kelvin. And then similarly, if we calculate the entropy for sink, right, or temperature S2 thermal reservoir 2, then the entropy will be Q over T, which is equals to nothing but 100 kilojoule divided by 600 Kelvin, right? So in that case, we'll get the entropy equals to 0.0166 kilojoule per Kelvin. So we can see clearly that S2 is this would be here, it will be 0.166. So we can see that clearly that S2 is greater than S1. So entropy is generated, and also entropy is for this system, entropy is increasing. So the first question was that what is the entropy change of the entropy in the two reservoir, right? So the change of the entropy delta S equals to S1 plus S2, which is equals to negative 0.083 plus 0.166, right? So which is equals to delta S equals to 0.083 kilojoule per Kelvin. So that's the change in entropy of the system, and we can see that this is a positive quantity, right? So that means that it's satisfying the increasing principle of the entropy, it also satisfy the satisfy the entropy principle, satisfy the increase of entropy principle. So that's all about this problem. So these two are the answer, right? So this problem is based on the topic 2 that we discussed in previous class, that entropy of a system, it increases if it works in between two thermal reservoir, right? Or it could be it could be equal to 0, but it's not possible that it will be a negative entropy will decrease of the system. So that's what the problem 7.21. Now we'll go ahead and do another problem topic based on the pure substance, right? So we talked about the topic 7.3, which was nothing but the pure substance, entropy change of a pure substance, right? So if any substance has fixed chemical composition, then we call that substance is a pure substance. So in this problem 7.31, I also choose this problem from the same textbook. It says that radiator of a steam heating system has a volume of 20 liter, right? So in this case, steam means that in this case it's a closed system, radiator is a closed system, and it is using water, right? It is using water as a working fluid. So it's saying that the the volume is 20 liter and filled with superheated water vapor, which is at 200 kilopascal and 150 degrees C. So let's say let's consider, I'm gonna go ahead and remove this thing to have more space. So at state 1 we have so at state 1 we have the volume. Let's use the state 1 we have the volume V equals to 20 liter, right? And then the condition of that vapor is superheated, and then pressure of that superheated vapor is 200 kilopascal, and the temperature of that superheated vapor is 150 degree C, right? At the same time, after the it says that at this moment both inlet and exit valve of the radiator is closed. That means it's a closed system, right? Closed system. And then after a while the temperature of the steam drops to 40 degrees C as a result of heat transfer to the room air. That means its heat transfer is happening, or heat transfer is happening here and temperature is decreasing. Determine the entropy change of the system during the process. So what is the entropy change, right? Entropy change is nothing but delta S times m times S2 minus S1. So S2 is the entropy of state 2 and S1 is the entropy at state 1. So at state 2 we have only the information about the temperature, right? T2 temperature was 40 degree C. So now to calculate the entropy change of that system, we have to have the information about the mass, entropy at state 2 and entropy at state 1. So let's go ahead and use the thermodynamic property table, how we can utilize this information to get those values. So for state 1 we need to have the entropy value, right? This S1. To get this entropy and other related information, let's use the table 1.6, because table 1.6 is nothing but superheated steam. So I already have those tables here. So I believe this one is here. Table A6. I'm using this, I'm bringing this table just to have your reference. So this table is let's use this table, right? So this table, you can see it's a superheated water, right? It's a superheated water, and we have the superheated water condition at 200 kilopascal. I think we have to take it a little bit more. Okay, so we have the superheated superheated water pressure at 200 kilopascal. That means that this one, right? um, 0.2 megapascal if we convert it megapascal, and then temperature is 150 degrees C, which is nothing but this line, right? Okay, the this 150 C here. So in this one we will calculate the entropy, we'll get the specific volume, and we also record the internal energy, right? So let's go ahead and grab all this information. So for state 1, from the table A6, right, from table A6, we have for T equals to 150 degrees C and T1, and P1 equals to 0.2 megapascal, right? We have the internal energy is nothing but 2577.1 kilojoule per kg. We do have the specific volume 0.95986 meter cube per kg, and entropy at that temperature and pressure 7.2810 kilojoule per kg Kelvin, right? So here is the important thing. So radiator, it's a closed system and it's nothing is changing, right? It has the the volume is the same. So that means that volume at state 1, specific volume at state 1 and specific volume at state 2, they're same, volume is not changing. So radiator has same volume, right? So that means that specific volume at 1 and specific volume at 2, they are the same. So 0.95986 meter cube per kg. Now at state 2, right, for state 2 we will gonna use the table A4, right? So let's go ahead and bring this table here. So this is my table A4, right? So table A4, I don't need all this information, so that's how I'm gonna crop it. So table A4, I need 40 degrees C, so which I have it here, right? So from this table A4, we'll take a look at this 40 degrees C condition right here. So what is the the entropy or specific volume of the saturated liquid and saturated vapor? Based on that, we'll calculate the quality of that vapor liquid system, or vapor liquid mixture. So at table A4 and state 2, the temperature at temperature 40 degrees C, we have the VF, or saturated liquid volume of specific volume of saturated liquid equals to 0.001008 meter cube per kg, right? And we have the VG, or specific volume of vapor, right, equals to 19.515 meter cube per kg. So now we have the specific volume specific. Also we got the v2 equals to v1, which specific volume v1 v2 they're the same, so which is equals to nothing but 0.95986 0.95986 meter cube per kg. So we have all those information. So we know that the v2 equals to we can write this formula vf plus x times vfg, right? So from here we can calculate the quality of the quality of the vapor liquid vapor mixture. So let's plug in all those value. 0.95986 equals to, we got the vf equals to 0.001008, right? And then v plus x times vfg is nothing but BFG is nothing but 19.515 minus 0.001008. So from here, if we calculate, use the calculator, and I already calculated this one, so x will be 0.049. So that means, meaning of 0.049 means that there is only 5%, almost 5% of vapor, right? And rest of them are liquid, so in this mixture. So this is the value of x. So now we have the x, so we using the chart we also should record at state 2, right? At state 2 we should also record the entropy, excuse me. So we also will also record the entropy right here, right here, right? So let's use that entropy value SF equals to 0.5724 and SG equals to 8.2526, right? So at entropy at state 2 we'll get SF plus X, which is quality of the liquid vapor mixture, and SFG, right? So in state 2 we have the entropy 0.5724 plus 0.049, right, times SFG is 8.2526 minus 0.5724. So if we calculate this S2, we'll get S2 equals to 0.9489 kilojoule per kg Kelvin, right? So what is the entropy change between these processes from state 1 to state 2? So the entropy change from state 1 to state 2 is nothing but mass times state 2 minus entropy of state 2 minus entropy of state 1. So we don't know about the mass, so we have to calculate the mass. However, in the previous class I told you guys that the specific volume is nothing but reciprocal of density, which is volume divided by mass, right? So unit mass. So if we want to calculate the mass equals to, it will be V divided by specific volume. So specific volume is not changing for state 1 and state 2, it's the same, and the volume of the system, so we have mass equals to volume divided by specific volume. In the volume of the actual system is 20 liter, right? And the specific volume for both of the cases 0.95986 meter cube per kg, right? The challenge is that here is the liter and here is the meter cube, so we have to convert that. So 20, if we convert this liter to meter cube, then we have to divided by 1000, so it will be 0.02 meter cube over 0.95986 meter cube over kg, right? So now we'll get the mass of the system equals to 0.021 kilogram only, right? So we have the mass, we have the entropy for state 1 and state 2. Now we can calculate the change in the entropy, right? Change in the entropy is 0.021 times entropy at state 2 we got 0.9489, and entropy in state 1 we got 7.281, right? So the total entropy change equals to delta S equals to negative 0.133 kilojoule per Kelvin, right? So this is the answer, the entropy change for the system, right? So now let's check the answer here. So here it's entropy change, it's 0.132, so we got 0.133, it's the same, right? However, one important thing is that this negative sign here, so the negative entropy, so in this case heat transfer is happening, and we saw that the temperature is changing from temperature is changing from temperature is changing from 150 degrees C to a temperature is falling up to 40 degrees. So it's losing the heat, so it's also losing the entropy. It's not, so that's why the entropy is decreasing. So that negative sign is meaning is that decreasing in entropy, that negative sign decreasing the entropy. But yeah, entropy, it doesn't mean that entropy is a negative quantity here, which will violate the first law of thermodynamics. So the total entropy generation, it's always positive or equals to 0, right? But it cannot be a negative quantity, which will violate the first law of thermodynamics. But here we got the negative. This negative is representing is the decreasing of the entropy. It's because of the decreasing of the temperature. So that's all about this problem. Problem 7.31 on the topic of 7.3 entropy of pure substance.